Hi, the finite element method is often used in engineering. This video is about how to compute the dynamic response of structures modeled with finite elements. Now, in most engineering applications, you cannot simplify a structure to a mass spring system or to a simple beam or bar. This is the case for aircrafts and cars, and also for curved structures in civil engineering where you need to use 3D kinematics. So what you can do in that case is to model the structure with finite elements. So let's take this example of a high-rise building, and it is represented by this model here, where the structure has been divided in several elements, in this case 11,700 elements, connected by nodes. And at each node there are several degrees of freedom that represent the motion. Here for beam and plate elements you have 6 degrees of freedom at each node, so in total 55,000 degrees of freedom. Now, what the finite element model does is that you can build the matrices K and M that link the motion at the different nodes. So it links the 55,000 degrees of freedom in this model through a large stiffness matrix and a large mass matrix. You also have a force vector that represents the force applied to the structure. So essentially, a finite element model can be treated as a multiple degree of freedom system, but where the number of degrees of freedom depend on the meshing. Now, with the mass and stiffness matrices produced by the finite element software, it's possible to use an eigenvalue solver and find the mode shapes and the associated natural frequency. For the building considered here, you see that the first mode is at 0.24 Hertz, the second one 0.27. You see that in the first one the motion is mainly in that direction, whereas for the second one it is in the perpendicular direction. The third mode is a mode of torsion of the building, and the fourth and fifth one are bending modes of the building. So second order bending modes, and these are first order bending modes. Generally in finite element software, the mode shapes are mass normalized so that mu I is equal to 1. Another example is a cantilever plate. So this is a plate of 1 millimeter thickness that is restricted at all edges in translation and rotation. Now we can mesh this plate with plate elements. Here we use 135 plate elements, and these are the modes and associated natural frequency. The first mode motion is shown here. This is the second mode motion, the third mode, fourth, fifth, and sixth. So you see that as you go up in frequencies, the wavelengths are becoming shorter and shorter. Now we have the stiffness and mass matrices, and we can compute the mode shapes. And based on that, we can just apply all the methodology that has been developed for multiple degrees of freedom systems to compute the dynamic response. So if we want to compute the response of structure modeled by finite elements, we can start with the mass and stiffness matrices, compute the mode shapes, and then use the orthogonality conditions to project in the modal basis. In practice, the number of degrees of freedom in the finite element model is dictated more by the details of the geometry, and so for large models it's not possible to compute all mode shapes. For the building we will not compute 55,000 mode shapes. In addition, traditionally the number of modes in the frequency band of interest is quite low, so we will use maybe between 10 and 50 modes. So in the end, we have a drastic reduction of the size of the problem when projecting on the modal basis. This is the example of our cantilever plate, where a force is applied at this location and the displacement is computed at the same location for an harmonic excitation. So we need to solve the following problem, and after projecting in the modal basis, we find this expansion, where here we have kept 25 modes in the frequency band from 0 to 100 Hz. So we see that we have all the resonance in this frequency band, which here are not damped because we did not introduce any damping in the equation of motion. Now, if you want to introduce damping models, you can use a C matrix, which, as in the case of multiple degree of freedom system, can be modeled with Rayleigh damping, where you assume that C is equal to alpha k plus beta m. And if you take beta x equal to 0, you have C is equal to alpha k, which is called a global viscous model. Now there is another way of representing damping through a loss factor. So if you write the equations of motion in the frequency domain, this is what you get. And for a loss factor, you assume that k is complex, where the complex part, the imaginary part, is given by the parameter eta, and this is the loss factor. So if you equate the two, you see that the damping matrix is now eta k over omega, so it is frequency dependent. This is why this is mostly used for frequency domain computations and not time domain. But overall, for all of these global models, it's always possible to represent them by this modal equation of motion, where the damping of each mode is given by psi I. So for Rayleigh damping, the modal damping is given by 1/2 alpha omega I plus beta over omega I. So by setting the values of alpha and beta, you have the modal damping of each mode. It turns out that for the loss factor, it's possible to have a very good approximation by putting the modal damping constant and equal to eta over 2. And in a more general way, if you want to specify the value of the damping for each mode, then you are in the more general modal damping model. Let's illustrate that on our cantilever plate. So here we are using an expansion of the equations of the response of the system with n mode shapes, where each mode has a specific damping psi j. So you see that we are using two different values. The first one is for viscous damping only, where beta is equal to 0, and the second one is a more general Rayleigh damping. So if you look at the values of modal damping, you see that for the first model, viscous model, the damping increases with frequency of the mode, and this is clear here because the lower frequency peaks are much less damped than the higher frequency ones. With different values of alpha and beta not equal to 0, then you have a more equal spreading of the damping, ranging from 1.5 to 3% in this case. We can also compare to hysteretic damping. So remember that if you take viscous damping, you have a damping that increases with the mode number, so with the frequency. And if you take hysteretic damping, you have a constant damping equal to eta over 2. So if you take eta is 0.03, which is the case in the graph here, you see that the psi is constant and equal to 1.5%. It actually matches the damping of mode 10 for the more general viscous damping, and this is seen here. You see that the two peaks correspond exactly. In finite element codes, it's also possible to specify local damping models. So the idea is that you can use viscous damping with a different coefficient alpha in each substructure. You can also use a loss factor with hysteretic damping with a different value of eta for each material in your structure. In general, this will lead to non-proportional damping, so that the psi transpose C psi is not diagonal, But if you assume small damping, you can use a modal damping model where your xi values will depend on the viscous parameters and the loss factors that you have defined. And you always have to remember that in practice, these values can be identified experimentally or from similar structures. So here again, projection in the modal basis allows us to compute transfer functions in a very efficient way. The same can be done for time domain responses, as illustrated next. As an example, let's take the response of a building to base excitation in the time domain, so with an earthquake excitation. So we know that the equations of motions are written in terms of relative displacement xr, and that the forcing term is minus the mass matrix times the acceleration of the basis, which can be written more generally as a transformation matrix T times a value of acceleration x dot dot 0. Then we have the following equations of motion, and we can project them in the modal basis using mode shapes with fixed base, so with x0 it's equal to 0. In this case, we end up with the following equation, and by using the diagonalization and assuming small damping, we can come with the following equation to solve for each mode shapes. So you recognize the modal mass, the modal stiffness, and the modal damping coefficient, and the excitation is given by a factor gamma I, which is the modal acceleration factor. So it means that we need to solve a set of equations which correspond to a 1 degree of freedom system excited by minus gamma I times the acceleration of the basis. One way to do that is to use the impulse response of each of these 1 degree of freedom systems and to convolute it with the base acceleration, so the modal acceleration factors. Then once we have the response for each mode, we can recombine by using all mode shapes and have the physical displacement at each degree of freedom in the finite element model. In the example of the 10-story building here, we see that there is a ground acceleration. So this is the Santa Cruz earthquake example, where ground acceleration is imposed at the basis of the building, and we are looking at the displacement at the top. So we are using 20 modes in the frequency band between 0 and 15 Hz, and each of them is assumed to have a damping of 1%. This is then the response, so the relative displacement at the top of the building, displacement between this point and the base as a function of time. So you see that when the earthquake arrives, before the earthquake arrives, you have almost no motion, and then starting around 10 seconds, you have an increase of motion. The first mode of the structure is at 0.8 Hz, and actually after the passage of the earthquake, you see that there is an exponential decay of the response, which corresponds mainly to the free vibration on the first mode. So it can also be shown on all degree of freedoms. So this is the video of the building excited by the earthquake. The time is given here, so you will see that as soon as you reach 10 seconds, the building will start moving. Of course, the motion is much amplified here to show you exactly how it moves. So you see that it will reach a maximum displacement here around 20 seconds, after which the motion will start to decay. So this is the free response of the first mode, where you see that slowly the amplitude of the response is decreased until it will reach the rest again after passage of the earthquake. The finite element method is extensively used in everyday practice for engineers. After meshing your structure, you end up with a certain number of degrees of freedom, and the software can build the mass and stiffness matrices. Based on these matrices, you can compute the mode shapes and natural frequency, and then perform a projection in the modal basis and follow all the methodology developed for multiple degrees of freedom systems.